First off, I wanted to talk about some misconceptions or some common ideas that people might have about machine learning that are not necessarily correct. So machine learning isn't really things like the Terminator or the Matrix or RoboCop. Like obviously these are like very like fun and entertaining new movies, but that's not really what I mean when I'm talking about artificial intelligence methods. In fact, these kinds of movies actually portray a lot of the common myths that people sometimes have about machine learning. So one of them is that machine learning works like a human brain. So it is true that machine learning methods are often modeled like loosely after like the neurons in brains, for example, but that doesn't mean that they're equivalent. AI generally is a form of computer engineering that is getting better and better at tasks that normally would require human-like intelligence. But there's also some tasks where humans can do something even at age 2 or 3 of like, for example, recognizing that something is a dog or a cat, whereas machine learning models require to see thousands and thousands of examples, whereas we can do it with 1 or 2 examples. So they can be complementary, but they're not equivalent necessarily. Another misconception is that machine learning can be 100% objective and bias-free. Unfortunately, this is not true. The machine learning methods that we develop can be just as biased as the people who actually develop them. And another thing that people will often say is garbage in, garbage out. If you feed your machine learning methods biased data, it will give you biased predictions. And so that's something to be really careful about. Another common misconception is that machine learning will replace more jobs than it creates. So according to several studies, AI will replace some jobs, but it will often actually create more jobs than it will replace. Okay, so now that we've talked about what machine learning is not and some common myths, what are some examples of machine learning that you may encounter in your daily life? So some things that you might encounter would be things like on your Apple iPhone, like your Apple Siri uses really advanced like natural language models to be able to answer things like what's the weather today or stuff like that. Amazon Alexa or Google Home are other examples of this. Another area where people are using machine learning a lot is in medicine. So for example, looking at x-rays of lungs and being able to classify whether a patient likely has lung cancer or not. You probably used Google Maps today to figure out where to have lunch. Well, that also uses machine learning methods. And then of course, people are very excited about kind of ChatGPT, the kind of recent developments in that. And this is also a form of really advanced natural language models. Okay. So let's talk about definitions a little bit. So generally, artificial intelligence methods are a set of computer systems that you can find in your phone or your laptop or even on a supercomputer that can do tasks that normally would require some kind of human intelligence. And then machine learning is specifically an application of artificial intelligence methods, which allows systems to automatically learn and improve from experiences without a human explicitly programming them to do exactly what to do. So often people will say AI when they're referring to deep learning methods. So that can be methods like neural networks, autoencoders, self-organizing maps, or some of the early kind of things before neural networks, which are called multi-layer perceptrons. The session on Thursday will focus more on those methods. For machine learning, people often refer more to things like Gaussian processes or k-nearest neighbors or random forests. So now that we've kind of have all our definitions correct, what are some kind of recent works that people have been doing in the area of radial velocity science? So we recently published a paper using fully connected and convolutional neural networks to model stellar activity in HARPS North radial velocities. Alex Wise, who will be serving on the panel as well, recently published a paper and also gave a talk earlier today, kind of highlighting some of his work. I listed a couple of other papers here as well, and I'm not going to go over each of them, and this is by no means like a full list, but this is just kind of like some of the recent cool papers that are using this kind of stuff. So I'll highlight a little bit of some of the work that we've been doing. So we were looking at using deep learning methods for Sun as a star radial velocities from the HARPS North Solar Telescope. And so we implemented 3 different kinds of neural network or somewhat simpler architectures. So these are kind of the 3 that we used. A linear neural network, if you want to even call it that, is essentially just like a linear regression method where you have like 0 hidden layers, you have like some kind of input, which in this case, we're using CCFs, which we heard a lot about earlier today. And then we're getting it to like try to predict what the stellar activity contribution is to a radial velocity. We also implemented a fully connected neural network where instead you have like each of those connections that you see corresponds to some kind of multiplicative weight parameter that is learned by the model from looking at a whole bunch of examples. And then like these hidden layers that you see kind of in the orange represents a hierarchy of like learned features. And then finally, the output layer generates those predictions. And then the convolutional neural network has some of the similar structure, but in addition to having those like fully connected layers, it also has convolutional layers, where each of these convolutional layers takes a discrete cross-correlation of the like input vector with the kernel vectors that the model learns. Something you might notice is that there's more sparse connections with the convolutional neural network compared to like all the lines or like more dense connections that you see for the fully connected one. And this is often thought to allow it to learn more local features that are like maybe translationally variant, for example, and exploit kind of spatial structure in data. So when we did this, we found generally that with the convolutional neural network, it performs the best. I'm not going to go into too much detail about this because I have a talk at 5 p.m. where I'll go into a lot of detail. But essentially, we were able to successfully reduce the HARPS North solar radial velocity scatter by about 40% or a factor of 1.7. And in this animation, you can kind of like see the neural network in action. So you're seeing like this residual CCF, which is essentially just looking at like shape changes in the CCFs. And then that's what the neural network gets as an input, and then it predicts this like stellar activity contribution. So we did some of this work with neural networks for solar radial velocities, but we also wanted something for extrasolar RVs instead. And so we developed kind of like a somewhat more simplified framework of using linear regression methods, but again, looking at shape changes introduced in the CCFs. And we were able to reveal the mass of a planet that was previously obscured by stellar activity. I'm not going to go into too much detail with these things, but I think generally what I would like to communicate is that, you know, with all of this, we really try to kind of look at what the gold standards are in the field of like using these kinds of machine learning methods and making sure that our models are not overfitting, our models will be generalizable, and you know, generally making sure that even when we're dealing with small data sets, we're kind of using best practices. So I'll kind of focus on that for the remainder of the talk. So one thing that's really key and kind of seen as the gold standard in these kinds of machine learning communities is to separate your data set into different subsets. So people will often have, if you have your 100% of your data, you might take 80% of that and put that into a training set, 10% into a validation set, and another 10% into a testing set, where the idea really is that you want to make sure that, again, your model is like generalizable and you're not like getting an overly optimistic view of how well you're modeling things because you're both training and evaluating your data on the same data set. So people will usually use the validation set to kind of like tune their hyperparameters. So in the case of like a neural network, that might mean like the number of layers you have or like the specific like dimensions of it or things like that. It might also mean like specific learning parameters like weight decay or things like that. In the case of like linear regression methods, it might have something more to do with like certain penalty terms. And then once you've done this like validation, people will like freeze their model and like not allow you to tune any more of the hyperparameters, and then finally evaluate it on this test set. And then you would write it up into a paper, hopefully. But yeah, so I think this is kind of what's seen as the standard. I think in EPRV science, sometimes it's kind of hard to do it this way, mainly because, you know, a lot of these machine learning methods are developed for like thousands of examples, whereas we're often dealing with maybe like data sets that are more in the hundreds or the tens or something like that. And so if you take, you know, a 10% of your data set, it's not always going to be representative of, you know, maybe the levels of stellar activity you might see or things like that. And so something that we've kind of tried to do is instead use like a cross-validation procedure where you're like having some like, for example, like 10% taken out and then training on 70% and kind of doing this all around so that your tuning is not hyper-tuned to just 10%, but to a larger swath of the data set. Okay. So one other thing that you can do to kind of make sure that your model performs well on new previously unseen data is using something called regularization. So this generally essentially will penalize really large weights, because generally if you see that your weights for certain parameters are like blowing up, often that means it's overfitting in some way. And so like, for example, if you just have like some kind of linear model, you might have like a loss function such as like your mean squared error, your RMSE, and you could add like a penalty term that has like P as your parameters, and then your lambda is going to be like the strength of the regularization, which is something you can tune as well. But yes, so I think another thing I wanted to briefly touch upon is kind of the different metrics that we used for model evaluation, which we'll have a very in-depth talk about as well from Sarah. But I think I just wanted to note that, generally we've often looked at like RMS or RMSE. Sometimes really great studies like this study from Lily Zhao have also like shown like different periodograms, or like, have this goal of in the future doing end-to-end injection recovery tests. But I think a lot of the time, sometimes these methods don't do a great job of making sure we're also prioritizing preserving planet signals, especially if we're just trying to go down and down in terms of RMS. So something we've been spending some time thinking about is whether we can create other kinds of diagnostic plots or other kinds of metrics that might allow us to kind of do both, driving down on the RMS, but also prioritizing preserving planet signals. So in this plot, what I'm showing is on the x-axis, a bunch of different methods for a specific exoplanet system. And then on the top panel, I'm showing what the estimated semi-amplitude is, as well as the uncertainty and the significance of the detection. And on the bottom panel, it's showing like the scatter metrics. And so you're both kind of keeping track of, okay, is this method like somehow leading to less significance in terms of the semi-amplitude? And is it also, or is it like just driving down the RMS and preserving the planet signal? So you might notice that there's also several different scatter metrics plotted. So the kind of darker blue one and the lighter blue one are kind of your standard ones where you have your raw scatter compared to like your scatter after applying an activity correction. And then the latter one is something new that we've been thinking about, where we're doing kind of like an unexplained scatter metric. So we're not only removing the predicted stellar activity signal, but also removing the RV from the modeled planets. Because what we want to know isn't necessarily like, what's the scatter when I remove stellar activity, but what's the scatter remaining when I've modeled all the parts of the system that I understand. And so this is kind of making sure that you're not just driving down to RMS because you're also removing planets, but making sure you preserve those signals as well. So with that, I will give some takeaway messages. So generally, we found that machine learning methods can systematically predict stellar activity contributions, both for these solar RVs as well as for the example of extrasolar data. Although it is true that machine learning methods do require a sufficiently large training set, neural networks often do not necessarily require dense sampling of the observations. Generally, another important thing is that formatting and normalization of your input observations and labels is really essential to making sure your machine learning methods can identify patterns and learn from your data. And it's also really important that these methods are evaluated on new, previously unseen data and implemented with regularization methods. If we don't do this, we don't necessarily know how well our models will generalize and how reliably we can actually recover masses using these methods. With that, I'm happy to take any questions.
Hi, a quick question. When you're training or designing machine learning models for the stuff you're working on, do you consider like interpretability of the layers or anything like that to be a desirable result? Is that important to you at all?
Yeah, that's a great question. So I think that something that we sometimes do, especially when we're like doing both like kind of a model selection comparison where we're doing like the fully connected, the convolutional and the linear regression method, is that we kind of use sometimes the weights from the linear regression method as a way to kind of also see like, does it seem like certain inputs are making a bigger difference than other ones? So I do think it's important that we kind of focus on explainability. We haven't done a ton of that when it comes to like the convolutional neural network architectures, but there are ways to do that, yeah.
Yeah, I was just curious. So I'm more familiar with this like training and test set, but haven't heard much about the validation set. And I was wondering if you could give an example of that, maybe in RV data.
Yeah. So I guess usually when people are doing like the validation set, the idea is that you would kind of tune your model parameters based on the validation set. So like say you have like, 60 RVs or let's just choose a simpler number. Say we have 100 RVs for simplicity's sake. Then like you would take like 10 of those for the test set. You don't look at them during any of your process, 10 of them for your validation set. The 80 that you have left, you would like, and you would randomly assign these. For the 80 that you have left, you would like train your model. Maybe if you're using machine learning methods, you might like change the specific kernel, for example, or maybe you'll change like the penalty term I was talking about with the regularization. Maybe you change the number of layers. Like you could change all of these different things, and you do that based on the validation set. So it's like, I guess the idea is that you have like this holdout set that your model's not being trained on, and then seeing how well it performs. Yeah, I hope that clarifies it. I think we might not have time for another question, but people can put stuff on Slack. Sorry, I just don't want to cut into other people's time. Sure, we can do one more.
It's all right, thank you. I just wanted to ask, for example, if you have training sets or that you're including different type of stars like M-Dors or K-stars, would it be able to separate in between them, or will it like create like any issue if you have, for example, some stars are more active than other ones?
Yeah, this is a really great question. It's something that we're actually looking at next. So I'll talk about this a little bit in the 5 p.m. talk as well. But it seems like from looking at different like of these CCFs like across the HR diagram, the patterns that we see are not necessarily the same, even sometimes for like relatively adjacent stellar types. So we're kind of like really trying to brainstorm like, whoa, does that mean that we need like kind of like custom models depending on the star that you're looking at? Or can we have something more generalizable, or do we need like additional inputs to be able to figure that out? So yeah, that's a really great question. If the next speaker wants to come up, that'd be great.
Hello. Good. Cool.
That sounds like it's doing better.
Okay. All right, you can hear me now? All right, great. My name is Sarah Blunt. I use she, her pronouns, and I'm a 4th and final year PhD student at Caltech. And I'm going to be starting as a Sierra Fellow at Northwestern in the fall. I'm going to be talking to you today about a predictive accuracy view of model comparison for astronomers. So just to situate what I'm going to be talking about in relation to Zoe's talk, I'm focusing on Bayesian model comparison. So the scenario where I have several different models, I run my MCMC or my nested sampling algorithm on each one, and I have a posterior, and I want to compare these posteriors for several different models and pick out the optimal model. Model comparison also isn't always about picking the best model, but just putting models on a common framework. But yeah, that's what I'm talking about. I also wanted to give a fun sort of historical note, which is that this is a talk I originally wrote at the very beginning of the pandemic because I was bored and I was trying to understand some notes from a Bayesian applied math class that I took. And over the years, it's sort of grown and expanded as I've learned different things about this topic. So this is definitely not a complete overview of this very large topic, but it's a fun like sort of history of the past 2 years for me. Okay, so before I get started, one last disclaimer. There are equations in this talk, but there's nothing written in equations that I'm not also going to describe in words. So if equations aren't your thing, you don't have to look at them. I include them because I think they're helpful in understanding what I'm talking about. Okay, so to first provide a little bit of motivation, Model comparison is a really canonical problem in exoplanet science, and I've given 2 papers that showcase different examples of the types of model comparison that we like to do in exoplanets. The first is thinking about how many planets are in my data. Are there significant eccentricity signals in my data? So highlighting this really cool paper from Rob Wittenmeyer about 2 circular planets mimicking a single eccentric planet. So that might be one type of model comparison you might like to do. Another one that we've heard a lot about over the past 2 days and we'll continue to hear about for the next couple of days is planetary signals versus stellar activity signals. So I might want to compare some metrics about which one your data look like. All right, so let's start off by deriving a natural comparative metric using Bayes' theorem. So if you have done any sort of Bayesian model calculation, model fitting in the past, you probably remember seeing that your posterior is equal to your likelihood term, the probability of your data given your model, times a prior term. And then it's divided by this term that oftentimes when you're first encountering this, people say, oh, you can just ignore that. That's just a constant. So that's the thing that we're interested in this case. This is the evidence term. So the Bayesian evidence is the probability of your data given your model. And you can think of this as just your integrated posterior. So you're integrating your posterior over your entire prior space. And I want to emphasize here that the BIC, or the Bayesian information criterion that you might have heard of before, is an approximate estimate of this quantity. So the Bayesian, this should be Bayesian evidence. The Bayesian evidence is, you can think of it as the total volume of the posterior. So like the average likelihood integrated over the entire prior space. So this is an interesting and worthwhile thing to compute. It's not always the thing that you might be interested in for your data. So since this is a talk that's trying to convince you that predictive accuracy is a worthwhile thing to also consider, I want to point out some of the cons of Bayesian evidence, or the Bayesian information criteria. So this is one way to quantify a model's goodness. Some cons of this are, first of all, that it's not always easy to interpret as an absolute metric. And what I mean by that is if you integrate your posterior over your entire prior space, you get a number. And that number is very useful to compare to other numbers. So if you have several different estimates of your Bayesian evidence or your BIC, you can compute a delta BIC and see sort of your best overall Bayesian evidence or BIC. But it's not super clear always to say, okay, my Bayesian evidence is 34. That doesn't necessarily tell you how good your model is overall. Another con that's not as much of a con nowadays as it might have been maybe if I were giving this talk a couple of years ago, is that the Bayesian evidence in particular is really expensive to compute. But this is becoming less and less of an issue because we've got really good nested sampling algorithms out there nowadays that give you Bayesian evidence for free. Okay, so I want to introduce you to out-of-sample predictive accuracy as an alternative to Bayesian evidence. And I'm going to show you this plot. Maybe plot is a strong word, drawn diagram a couple times throughout this talk. So I'm going to spend a little bit of time emphasizing it right now. So on the x-axis, I have model complexity, which you can think of as approximately just the number of free parameters in your model. And on the y-axis is your prediction error, so how well your model fits your data. So you could think of this as like a mean squared error, for example. And then I'm showing 2 different curves. One is for in-sample data. So this is the data that you're training your model on. And one for your out-of-sample data. So connecting back to a process that I'm guessing a lot of us are familiar with, like running your MCMC on a set of data, the in-sample data might be the data that you're actually running your MCMC on. And then the out-of-sample ones might be things that you try to predict with your model after the fact. So you can see there's this characteristic behavior that as you increase your model complexity, as you add more free parameters, typically your in-sample prediction error gets better. You definitely have diminishing returns as you get to higher and higher model complexity, but generally the more free parameters you throw at your model, the better you expect your in-sample prediction to be. Out-of-sample prediction, on the other hand, has this U-shaped behavior. So when you're underfitting, your out-of-sample prediction could be better. So you could get a better fit by adding more model complexity, more free parameters. And then at a certain point, it turns over and your out-of-sample predictability starts to get worse. So the point of using predictive accuracy to do model comparison is to try to find this like 0 point of your out-of-sample prediction error. All right, so how do we do that? Let's define a metric. So we are going to define this thing called the log pointwise predictive density as our goodness of fit metric. So focus on the first equation at the top here for a second. This is the probability of new data points. So here I'm denoting new data points as y with a little tilde on top, given your existing data points. And you're summing that log probability over all of the new data points that you have. So in order to do that, I have to expand out that term, and I get the second line in this, which is I'm integrating it over the entire posterior. So integrating it over all of the combinations of model parameters, which is denoted by theta here. So the key takeaway here is that the metric that I want to compute is how well I can predict new data points given my existing data points. And I can do this by computing this quantity, integrating over the entire posterior. But there's a catch, which is that not all new data points are equally probable. There's some underlying physical process that's generating new data points and makes it so that what we really want is not the log pointwise predictive density, but the expected log pointwise predictive density. So the point here is that we don't necessarily want to calculate we don't necessarily want to weight every possible data point equally. We want to weight the ones that will actually have a high probability of occurring given our underlying physical process. So the only difference between this metric and the metric on the previous slide is that I've now added in this term p true, which is the probability of this new data point actually being drawn. So you might be wondering at this point, okay, how do we actually calculate that? Isn't the whole point of model comparison or model fitting in general that we don't know p true? We don't have a model for the underlying physical process that's generating new data points. And you're right, but it turns out that there are a bunch of approximations for this that can be proven to converge to this estimator in a bunch of different, with a couple of different assumptions. And in order to understand how this works, we need to go back to this diagram of model complexity. So the two metrics that I'm going to focus on the most in the rest of this talk are the AIC and the WAIC, which I like to call the wake, which I don't know if that's legit. These both use the same logic to estimate this ELPPD. So just quick review, the ELPPD is trying to estimate how well your model is going to perform on new data given your existing data. So it's sort of an average of how well your model predicts new data averaged over your entire posterior sample. So these both use this logic of estimating this quantity by having an estimate of the in-sample predictive accuracy and then subtracting off an overfitting correction. So going back to this diagram here, the idea is that if we're here in the model complexity diagram, we calculate the in-sample prediction error or log pointwise predictive density, and then subtract off some estimate of overfitting to get to our out-of-sample prediction error. So even though we don't actually know p true, we can use the fact that these data points that models tend to follow this, this curve of prediction error in order to figure out a very good estimator of our ELPPD. I also want to mention, since BIC is in the title of this talk, that the BIC does not seek to do this. So the AIC, which is very similar to the BIC in terms of your actual formula, tries to do this. The BIC doesn't try to do this. The BIC is an approximation of the evidence. Yeah. Okay, so let's talk about the AIC first. There's an extra factor of 2 in front of the K, so sorry about that. The tagline that I came up with for the AIC is "My data are very good." So the way that the AIC wants to predict this ELPPD quantity, so it's going to follow the same logic of first trying to get an estimate of the LPPD, the in-sample predictive accuracy, and then derive some sort of overfitting correction. So it predicts the in-sample accuracy using the actual computed in-sample predictive accuracy of the maximum likelihood estimator. So you have an entire posterior, you just pick out your max likelihood model, you use that to compute how well your data fit the in-sample points, the ones you trained on. And then the overfitting correction is K, which is the number of free parameters. So the idea here is the more free parameters you have, the worse your AIC is going to be. And if you stare at this for long enough, you can start to see why the AIC requires your data to be very good in order to work. First, remember that we're trying to compute an average quantity over the entire posterior. So if you're only using the maximum likelihood estimator to compute this thing that's supposed to be an average, the idea is that your maximum likelihood estimator has to be pretty representative of your whole posterior. So you can think of it like you need your posterior basically be like a delta function around your maximum likelihood estimator. So typically people say that you need your posteriors to be relatively prior independent and relatively Gaussian in order for the AIC to give you reliable results. Okay, another technique or metric I want to introduce you to is leave one out or cross validation. And the tagline of this one is why approximate when you can brute force. So you might be saying, okay, I want to measure the performance of my model on new unseen data points. I could just compute that. I could just, take every single model in my posterior or some large statistical sample of my posterior and actually compute the log point-wise predictive density of new unseen data points, which already have this p-true probability baked in because they're new data points. They actually have been generated from this underlying physical model. So that's all that this does. The sort of clearest drawback of this is that it's really computationally expensive. There are some issues with choosing the data points that you want to perform your leave one out or cross-validation estimate on. And this is particularly true with EPRV where like cadence really matters. I'm happy to talk about that later if people are interested. Another drawback of this is that we don't always have the luxury of lots and lots and lots of data points, as Zoe mentioned. So one example that would be absolutely crazy in like, in the broader field of machine learning, but is totally reasonable in exoplanet studies is like, okay, I have 4 RVs and I want to do model comparison. If you want to do leave one out, you're going to get really different results every time because you're leaving out a completely different 25% of your data points every time. So this is not always possible, but it's worth mentioning. All right, and the last one I want to talk to you about is the WAIC, or the widely applicable information criterion. And this one, the tagline that I have is, I have a posterior, but I don't have data or CPUs to spare, meaning that doing cross-validation is something I don't really want to do for whatever reason. So we're going to use the same the same approximation or logic to compute the ELPPD estimator. So the first term, remember, is your estimator of the in-sample predictive accuracy. So the idea of the wake is, okay, let's just brute force calculate that. I have all my in-sample data points. I have a posterior. I can just, for every sample in my posterior, I can actually calculate the predictive accuracy. And that's the common thread through all of the different formulae calculating the wake in the literature. The overfitting correction, there are several different ideas of how to do this. One that I tend to use a lot and that I think makes sense is the sum of the variances of the in-sample predictive accuracy of existing data points. So the idea behind this formulation is if your model is overfitting, you're going to have a much smaller variance in the predicted accuracy for your in-sample data points. Whereas if you're underfitting, you might have a lot more variance in your posterior predictive accuracy measurements. All right, so that's pretty much it. The summary of this is that we can derive criteria like the, I was going to say AIC and WAKE as estimators of the out of sample predictive variance. The BIC can't be derived this way, but is an estimate of the Bayesian evidence, the probability of your data given your model. And I think if you take away nothing else from this talk, I think it would be really cool if more people thought about leave one out and cross-validation and the wake in the context of Bayesian model comparison. I think our field can explore it more. And just to finish with an advertisement, if you really like model comparison, I've got a paper coming out using VLTI gravity, which is an optical interferometer. I know nobody in the audience cares about direct imaging, but I have the floor for another minute, so I'm going to force you to listen to me talk about it. And I think this system is cool because gravity is really cool, optical interferometry is really cool, and it allows us to get an eccentricity of an object that's 100 AU away from its star. And I think this paper would be of particular interest to people in the audience because not only do I calculate a bunch of different model comparison metrics, I'm able to sort of explain why they're different. And so going back to the sort of intuitive understanding that I've outlined in this talk. And two more little advertisements. One, everyone should watch out for Ryan Rubenzahl's upcoming paper on the mass radius relationship, which also uses a ton of really awesome model comparison metrics. And then I beg of you to wake up at 9 a.m. tomorrow and you can come see my talk about V1298 tau and cross-validation. Yeah, and I put up some sources because I'm assuming that eventually these slides will be posted somewhere. And yeah, I'll leave up my summary and take questions.
Hey, Sarah, super great talk. I'm sorry if I missed it at the end there, but could you talk a bit about why someone might not want to use the wake?
Yeah, I didn't really talk about it at all. I don't really have a good answer. I feel like the wake is always a good thing to do. If people in the audience have ideas, please shout them out.
On this point exactly, you mentioned that you were using the sum of variances as an overfitting correction, so the first term has no units, right? The LPPD, it is a unitless term, right?
Sorry, I didn't get that. What'd you say?
The LPPD, it has no units. It's like it's a log-like field, so it's not in a specific unit.
Sorry, my brain isn't working.
And if you use the sum of variances as overfitting correction, the variances, they have a unit. They are in meter per second squared. So, I mean, you have a sum of a term which is in meter per second squared and a term which is a log likelihood. So basically my question is how do you account for the fact that they are in different units, these two terms?
Oh, it's not, I would just look up the equation in the literature. There's ways to put them on a similar scale, basically.
Okay,
Yeah.
Thanks.
Sorry, it took me forever for my brain to interpret what you were saying.
Hi, Sarah, great talk. You implied that perhaps there are reasons why we might not wish to use the BIC or the fully marginalized likelihood, but in principle, in perfect world where all of our assumptions are correct, they should be equivalent to these other metrics you're talking about. So what assumptions fail to make us want to use these other ideas?
Yeah, it's an interesting question. I also didn't mean to imply that you shouldn't use the Bayesian evidence ever. I think one particular regime that I could bring up is that the Bayesian evidence can be pretty prior dependent. So imagine that you have a really big prior where a lot of your prior space ends up not being physically reasonable. And you end up having a very small likelihood there. So you wouldn't necessarily say that exact model is correct. But if you have this wide swath of prior space that has a very low likelihood throughout, that could end up upweighting your Bayesian evidence. So I think maybe it's a bit of a contrived scenario, but I think in this field, we're very concerned with physical realism. And I think this is something that happens a lot. I think also the point to make is that going back to my point about physical interpretability, I think the Bayesian evidence to me is at least is less physically interpretable. Whereas your prediction of how well you're performing on new data points is a little bit more interpretable. Yeah, great question.
Okay, fantastic. Oh, I want to not drop this. What did I do? How did that happen? Okay, there we go. All right. Thank you very much, Zoe, and oh my gosh, I blanked on your name. Agustín. Yeah, sorry, I have a very bad brain thing with names. Anyway, thank you very much for giving me the opportunity to give a talk about Gaussian processes and precision radial velocities. I'm giving this talk on behalf of my former boss, Suzanne Agren, and so that comes with a couple of caveats for this talk. So firstly, this is a very heavily biased talk towards Suzanne and her minions, her group. So it does have a heavy bias towards that work in the field. So by no means is this comprehensive. But also, this is sort of a fun opportunity of taking a look back at where Gaussian processes in radial velocities came from. I also say former boss. As of last week, I stopped working. I was a postdoc with Suzanne in Oxford, and as of last week, I am now a postdoctoral research fellow at University of Southern Queensland. But I am taking off my Queensland hat and putting on my Oxford hat for this afternoon. So as I said, we're taking a bit of a historical journey here to the tale of Koro 7. So this was a transiting planet found by the Koro satellite. And Koro found a handful of interesting transiting planets. And at the time, people were really excited to follow these up and try and measure their masses so that we can do atmospheric studies and all of the fun things that we get to do today. But Koro 7 is active. As you can see from this light curve, it has bumps and wiggles. The arrows are not pointing to the transit. They're pointing to points where they've used to measure the rotation period of this star from the light curve. It is quite active. And so this presented a really big challenge to then do radial velocities. It was hard. You had a whole lot of teams trying this with different instruments and different techniques to be able to remove or try and mitigate all of this stellar activity in the radial velocity data set to be able to then measure the mass of this planet. And what ended up happening was that you had a whole lot of different techniques, a whole lot of different data sets, and you also ended up with some variation in the mass estimates and even in the number of planets discovered. So you had Koro 7b, which is the transiting one, but then also in the data set, you have additional signals of non-transiting planets. So it was through working on this problem of trying to disentangle activity. So you have in these various papers, you have methods that are looking at sort of pre-whitening and harmonic filtering, and then also going from the other end of going, okay, spot models, if we model the spots and then we try and estimate the RV variations that way. But they're both quite challenging. So then along comes Agren, Pont, and Zucker, and with the FF prime method of estimating activity-induced radial velocities from photometric data. So it works on the principle that you have the spot-induced radial velocity signature acting as a function of the derivative of your photometric change. So here you have a nice example of, here is the variation in light due to the spot, and then you take and then you see below the variation due in the radial velocities from that spot, and you can sort of see by eye to first order, you have this acts as the derivative of the derivative. You also have some term in here for the suppression of convection, and that scales as the flux squared. So here we have a nice simple estimate for radial velocity variation due to photometric variation. So then back to the tale of Koro 7. In Hayward 2014, they take Harp's velocity and simultaneous photometry to then implement this FF prime method. And in order to do that, in order to calculate the derivative of the light curve, they needed to smooth it somehow. And they did this with a Gaussian process. Now, the fun little story that comes with this is that Suzanne was the reviewer of this paper. And she got this paper and was like, wow, this is really cool data. And said to them, hey, have you tried using a GP on this? And then I believe Rafi and Suzanne sat down at a cafe on laptops and proceeded to then implement the GP on this data. So this is, we're not quite there yet at the RVs on radial velocities just yet. But we have now starting to use the Gaussian process. So this is a good point to give a bit of an overview of what a Gaussian process is. I'm sorry, there is an equation. Actually, no, there's another equation too. I'm sorry. But I promise you there is a good reason for having them. So this is a nice sort of example. Well, this is essentially what a Gaussian process is. If you've got a data set, you're not fitting a functional form to this data. Instead, you are modeling the correlation between your data points. You're saying that there is some process, some Gaussian process that your data is pulled from according to some correlation matrix K. That correlation matrix, the form of that gets governed by a kernel function. And then you also have a mean vector M. So this mean vector can be anything from, say, a linear trend in your data from something that you already know about, or for example, in radial velocities, we use a Keplerian. So you know that there's planetary signals in there, depending on the data, and you incorporate that into your Gaussian process by this mean function, by this mean vector. So Haywood et al. Used the quasi-periodic kernel, and this is one of my favorite kernels, and it's a lot of people's favorite kernel because it is nice and intuitive. You have these 4 hyperparameters that we care about, so that the 4 things that govern how this kernel behaves. You have the amplitude, which is broadly represented by the amplitude in your data, by the variance of your data. You have a period that corresponds to the rotation period of the star. And you have this evolution time scale, which corresponds to some evolution of the surface features of your star. So you have a quasi-periodic signal here. You have something that is periodic, but also decays over, where the signal decays over time once you get too far past your initial data point. You also got this harmonic complexity term, and this is, I would say, the least intuitive of any of the terms in this kernel. Exactly what determines your harmonic complexity is a matter of some study. It essentially, to get a feel of what it is, we describe it as the number of bumps and wiggles per period. So how complex is your data within one period? So I mentioned, period corresponding to stellar rotation period and evolution timescale corresponding to some sort of spot evolution. We did the tests on this, and it took me way longer than I thought it would to get this paper out over something so simple. There were more tests that we did, but yes, to make sure that we got it right and we were understanding what we were doing, we do see that from stellar models, the GP period matches the input period of the stellar rotation, and similarly with the spot evolution time. So it's nice. This is a nice physically intuitive kernel, and so a really nice one to use on stellar data. So back now to the tail of Coro 7b. We have this GP that we're using, a quasi-periodic kernel, to model out the variations and smooth the variations in the light curve and apply the FF prime. But what they found was that wasn't enough. There wasn't enough activity removal from that method alone. There was something else that was happening. There were other processes in the radial velocity data that were not being fully covered by just that FF prime. So then they added another GP onto the radial velocity data to account for this difference. And this is where we have our first implementation of Gaussian processes in radial velocity data. So this is exciting. This is now an exciting new tool, and people saw it, took it up, ran with it, and here we are today. Some evolution from there towards now, we then come to the multi-dimensional Gaussian process. So this is where, rather than just using the radial velocity data alone or using photometric data, it's often quite difficult to get photometric data simultaneous with radial velocity data. In fact, it's very uncommon and frustrating in terms of applying for telescope time. So what we like to do is be able to use activity indices or some sort of activity metric that comes from the spectra itself. So from the same observation, from the same photons that we use to measure the radial velocity, to also measure the activity-induced radial velocity change. So this is where we have things like activity indices, so spectral features, the change in spectral features in your spectrum, and things that come from your radial velocity measurement itself. So like your, it says CCF-BIS, which is very helpful. That is the cross-correlation function bisector inverse slope, which is just a measure of how much your nice absorption line is curving or bumping or wobbling. So Rajpal et al. Wrote out this formalism for being able to take to be able to incorporate these other activity indices into your GP. So what you're essentially doing here is that you're taking a GP that is some latent process. You've got some mysterious Gaussian process that's happening, and you're saying that all of these things are a result of that Gaussian process, and being able to combine them together in this way. So in this way, you're able to essentially train your GP. You're treating your GP like it's, you're training your GP on activity-related things that don't have any planet signals in it. So therefore, when you apply that to your radial velocities, you're not accidentally pulling in other signals that you don't want. So going forward, then we have now sort of three-dimensional GP, but we can actually take this into as many activity indices as you want, try and cover many different things. And so this was in the Pianetti paper. So Oscar Barragan in Sutherland's group has this beautiful program called Pianetti, where you can do all sorts of wonderful, fantastic things with your radial velocities and your transits. You can simultaneously model them. You can also include as many different activities indices as you want. You can also include different telescopes, and in that way, be able to nicely model radial velocity data. And for nice evidence of how powerful this multidimensional GP can be, we have been able to find planets and measure the masses of planets around very active stars. So this is the example of K2-100, which is a young system with planets. With a small, you can see from the red line, a much smaller amplitude planet signal than the activity, but with using this multi-dimensional GP, being able to pull that signal out. It works really well, particularly for young stars, which as someone who used to work on young stars is very exciting, because this is great parameter space for us to be able to understand planet formation. And we can do it because we now have the tools to be able to see beneath this activity. So I mentioned before, the importance of going from the 1D to the 3D. So going from the simple, rather than just using the radial velocities, incorporating other activity indices as well. And this is a really great example of just what happens. So as you increase the number of activity indices, so you've got the different histograms, it might be a bit hard to see actually. So you've got one line where the dark line where it's just the RVs, and then you've got a colored line where it's the RVs plus 1, so the 2D, so it's the RVs plus the full width half max. And then you've got the filled in histogram where you're using the RVs and the full width half max and the bisector inverse slope to be able to better characterize the activity. And that way actually get a much better estimate on your mass measurements. And keep an eye out for this one. This has not been published yet. It has been submitted to MNRAS. I think the corrections are done, and I think Oscar's going to put it on the archive today or tomorrow. It depends on when he finishes his ESO proposals. So yeah, so that's one example. Of course, I mean, multi-dimensional GPs, there's quite a few out there, and quite a lot of development in GPs in general with making them faster. And a great example of that is the S+ Leaf, as well as Celerite and TinyGP and a whole lot of other packages out there that are making GPs faster. It's a problem that the more data you have, the more computationally heavy a GP becomes. And so making them faster has been really powerful. And if you go and check out Houchuan Mu's poster number 84, he's done some work now that we have this much faster GP to use, this much faster implementation. We can now start using bulk data. So we can do it on multiple stars very quickly. To finish up with, I've got a lot of open questions and future directions here, because it's Gaussian processes are such an exciting and powerful tool, and they offer a lot of exciting opportunities and also a lot of exciting challenges. So a major part of the process is understanding your activity indices and understanding how they scale with your Gaussian process, whether or not they scale as g squared, or as g, or as g dot, or as g double dot. Understanding how that relates to the underlying process that you're probing. It's also interesting looking at, as we move forward to really long surveys like the terror hunting experiment, things that are happening over decades, how do we deal with data sets that go for that long? How does our, are we going to be how do we allow the GP hyperparameters to evolve just like the stellar cycle evolves? Another interesting aspect, one that I've been interested in, is the physics of kernels. So the kernels themselves, a lot of them, like the squared exponential, they're maths, but they're nice maths. They're useful maths, but is there any physics that can be gleaned from them and from other kernels as well that people use? I've mostly focused on the quasi-periodic, but there are quite a few kernels out there that you can use. Some more or less physically intuitive, but can we glean some intuitive physics from it? And then also on the other side of that, can we use physics? Can we use our understanding of stars and how stars behave to then create a physically motivated kernel? Create a kernel that is especially for stars. All sorts of other things that are in the GP land, using a Gaussian process applied to the CCF or to the whole spectrum. Lots of people that have been working on that. Vinesh Rajpal has been working on this, and Hao Chuan is also working on this. And then also not just looking at probing the typical stellar activity, but also using Gaussian processes to look into things like granulation and supergranulation, some of the other things that we have to care about when we get to really precise RVs. And with that, I will open up for questions. Thank you.
Thanks for the great talk. So because this is a machine learning Splinter session, and now that you mentioned GP, so I wonder if you have actually do a train test split in a GP. Let's say you have a training data set and you train a GP model and then test if the GP model can recover the data in the testing set.
I guess so. So I don't quite understand. I think so. If you're asking in the sense of testing whether or not you get out the same hyperparameters from the GP from different data sets, or
let's say you have a time series, RV time series, and you want to use GP to model the stellar variability RV and the planetary RV at the same time.
Mm-hmm.
But let's say your model gets overcomplicated and overfeed the data, but you don't know whether it's overfitting. And that's why you would need the train test split to see whether the model is robust even in the testing data set that it's not trained on. Does that make sense?
Sorry, I didn't quite hear the last part of your question.
Oh.
The speakers are all facing that way, and so I actually can't hear very well when they're coming out of the speakers, but I don't want to step in front of that because then that makes loud noises.
It's basically a concern of overfitting the data.
Overfitting,
with GP.
yeah. No,
so
that's definitely a risk.
So is that worth considering, like training the GP on the training data set and then doing a validation or testing?
Yeah, I guess this is where you're training your data on things that are not your radial velocities, but you're fitting your radial velocities. So you're training your data on something that is not, what you care about is the fit to the radial velocities, but you're training that underlying Gaussian process on things that are not the radial velocities at all. But I can understand what you mean by overfitting. I think there are ways of making sure that that's not the case, but they're separate.
Hello.
So I'm Barak, I'm coming from gravitational wave data analysis, and specifically regarding one of your open problems about what to do when the GP changes or evolves with time. So in gravitational wave data analysis, there's the power spectral density of the noise that changes as a function of time. And it turns out that there's an easy solution to small fluctuations in the power spectral density or in the GP, which is that the first order error in any likelihood estimate that you do with the Gaussian process is actually correctable by a single scalar that you can track. So instead of varying the GP hyperparameters, you can just track this single scalar. I can give you a reference if you want.
Yeah, no, that'd be cool. Thank you.
It's not really a question, it's more of a claim. The harmonic complexity is related to the stellar inclination.
Is related to the
Stellar inclination.
stellar
Inclination, like the
inclination.
inclination of the star with
Okay.
respect to the observer.
Yeah. I would say it's also, I think it's ridiculously complex. Because I've also found that it's strongly related to the sampling and noise in your data as well. So if you have a perfect data set, sure, yes, I could imagine that it would be related to the inclination.
It's also related to the Lim-Darkening law.
But yeah, when I tried to see correlations between harmonic complexity and other things, as soon as I added noise to the data, it was just the noise. Like, yeah, it's disappointing.
Give one to them, yeah. Oh, I think it's just a 4 of you guys, yeah. Is this working? Yes, okay. So we have a couple of like questions for you guys just to kind of get the discussion started, and then we'll be happy to like have audience members ask any kind of like broader questions. So, you don't have to answer every single question, but if you have something that you want to add, please do. So we can get started with the first question. So what are some statistical or machine learning methods that you guys each think are the most kind of promising for EPRV science?
I guess I'm starting by virtue of holding the microphone first. Yeah, I think we've been hearing about a lot of really interesting machine learning and data-driven methods during this conference. I'm going to be talking a little later about modeling stellar variability in the full spectrum. And I think that a real power of these machine learning methods is the ability to treat really large data sets, including looking at, say, every pixel in the spectrum or every stellar line. And I'm especially excited, I think, about how machine learning technology has really pushed forward optimization of extremely large models with lots of free parameters. So something that that I used for the Wobbly code and that Zoe mentioned in the context of Michael Gully-Santiago's work on the Blase code was backpropagation. So doing optimization problems that use the derivative of the likelihood with respect to free parameters to make exploring parameter space much faster and more efficient. I think that even without using something that is necessarily referred to as machine learning, we can still build much more complicated models and actually have a hope of using them well, thanks to tools that have been developed by the deep learning community.
Introduce yourselves if you're joining the panel.
Oh yeah, sorry. So I'm Megan Bedell. I'm an associate research scientist at the Center for Computational Astrophysics at the Flatiron Institute.
I'm Sarah Blunt. You just heard me talk. Yeah, I definitely agree with everything that Megan said. I'm a big fan of Gaussian processes, and I also don't think that Gaussian processes are going anywhere in the field of stellar activity modeling anytime soon. But I agree that it seems like there's so much information in the spectrum that we're not taking advantage of. And yeah, I guess something else kind of random and out there that I think would be cool to think about as a field is, I did an internship at Google over the summer, and Google's really interested in fine-tuning large neural networks. So this is the idea of taking a pre-trained neural network and fine-tuning it for a particular task. So if you have, like, for example, a huge language model that's trained on all of the internet data that exists to, like, fill in the blank in a sentence, you could then fine-tune it to predict like how engaging a web page is, for example. So a particular task that it's not necessarily trained on. So I think that there's room in the exoplanet community for not just like training a neural network to understand like one particular spectrum or one particular star, but thinking of building up like, you know, a library of all different types of stellar variability and stuff in the spectrum that can then be fine-tuned for individual stars. So I don't know.
Hi, I'm Alex. I'm a postdoc at Penn State University. Yeah, I agree with what they said, and also I guess I just want to emphasize that, like, I think really pushing the boundary of improving our ability to correct for stellar activity is going to happen at earlier stages in the pipeline than I think a lot of people are working at. I think sort of Gaussian processes are great for sort of analyzing your results after the fact, but yeah, like, you throw away so much information just by making a CCF that I think is going to be required for these machine learning methods. So I think the question was actually which machine learning methods, and to that I say whatever you think is interesting. I think we should just try out a bunch of them and see what happens.
Hi again, I'm Belinda from University of Southern Queensland / Oxford. I really like the idea of physically motivated kernels, mostly because I'm also a stellar physicist, and I mean, most exoplanet people are stellar physicists in disguise. So I really like the idea of having something that can actually tell us a lot more about stars and help us understand stellar physics better, and as a side effect, help us find planets more easily. So I think for me, that's, yeah, being able to find these more clever ways of being able to get more information about the star out of our spectrum and out of our data. And I think, yeah, some sort of physically motivated kernel, be it yeah, on the spectra itself or on some sort of data product from the spectrum, I think that'd be really cool.
Awesome. I'll ask one more question and then open it up to the general audience. So what do you guys think are like some common like pitfalls or like concerns that you have about people using these kinds of either statistical or machine learning methods for EPRV science?
Do I start because I'm holding the microphone? Blindly applying these things without thinking. I think that's a pitfall that we can all fall into all the time. Yeah, I think you should really know what, yeah, garbage in, garbage out. You need to know what you're doing with it so that you can actually properly interpret the results that you've got. I think that's, yeah, it's sad because it's hard. You can't just like pick up the Celerity package and throw your data at it and hope that what you get out at the end is exactly what you want it to be. I think it's, yeah, you just have to be careful. You have to test, lots of tests. Yeah.
Yeah, I'll add to that. I think interpretability is kind of something that people think they're going to be able to do a lot of times ahead of a project. And then the more they understand the project, the less interpretable they realize it actually is. So that's one of the pitfalls of a lot of machine learning methods, especially one that I've worked on with deep learning, where, you know, we can look at the results in a lot of different ways and we can try to interpret, you know, how good they are. But at the end of the day, we don't really know what it's doing. And I guess there are methods actually for sort of looking back at the convolutional layers and figuring that out. But the impression I have of that is that it's difficult. And so I haven't worked on it with the projects that I worked on. But yeah, I think it, you know, there's always a place for sort of, you know, equations and physics and trying to incorporate those as much as possible into your method to enhance interpretability. And when you can't do those, I'm just, being careful.
This might shock you, but I agree. And I also think that interpretability is a really big deal. And in particular, I think one thing to sort of caution people about is that a lot of the machine learning literature is like developed with a different goal in mind than science in a lot of cases. And this is the goal, I think, of a lot of machine learning projects is to reproduce new data. And that's, I think, something we're interested in as a sort of metric of success in science, but our ultimate goal is like physical understanding and like deriving, you know, the underlying physical process or law that governs the creation of this data. Yesterday I was giving a practice talk and was it Corey? Was it you who asked this question about like, well, you know, the difference between that graph that I showed of your in-sample predictive accuracy versus your out-of-sample predictive accuracy. Corey was like, well, you don't really want there to be any difference between your like in-sample and out-of-sample predictive accuracy. Like if you have sort of the right underlying physical process, then you should be able to like perfectly, or, you know, within your noise, like predict out of sample data points. And that's a really good point. So we sort of have a more lofty goal in science than just minimizing our out of sample predictive accuracy. We want to get at the underlying physical process. So I think that's sort of a philosophical point to keep in mind when you're reading some of this literature, is that our task is harder.
Yeah, I think the main points that are emerging here about carefully testing your models and building interpretability and are kind of maybe the two key things. I guess what I can maybe add to this is an illustrative example of one of the ways that this can be really tricky. So some work that I was doing with Lily Zhao that I'll talk a little bit more about later, trying to learn from in a data-driven way, the kind of vectors along which a spectrum can change due to stellar variability. We were developing this model initially, and one of the first tests we wanted to do was to simulate stellar spectra with a star spot moving across it. And so we were using the kind of field standard data that we use for this, which is the Kit Peak solar atlases of the quiet sun and a spotted sun. These are built into the back end of the SOAP tool, if you've used that. But one of the little gotchas that we realized partway through developing this test is that the observed spot spectrum is about a signal to noise of 200 or so. And so when we were in best case scenarios modeling very low noise level observed spectrum, we were inserting this spot signal that would be Doppler shifted along the spectrum, and we would end up inserting both the stellar features of the signal and the specific realization of photon noise that is in the Kit Peak atlas. So if we were to take a set of this, and because we were using a data-driven model, it has the freedom to latch onto those photon noise wiggles as a feature that it's learning that says, oh, if you have this photon noise realization, that means you're observing a spot. And so we could hold out validation and test data from the simulated spectra and use that to evaluate our model, but that wouldn't actually show this problem until we tried to move to real data or data with a different realization of noise in the spot spectra. And fortunately we realized this and we're able to design new tests to fix this and to train our model on data with different properties. But this is one of these kind of gotchas where you can like easily think that you're doing all of the best practices in testing your model thoroughly, but because you're kind of allowing the model all of this flexibility, you can end up learning things that are physically meaningless and will not apply to your next data set. So in the interest of open sharing, maybe you guys have run into this kind of issue too, but that was one of the sort of things we had to be very careful about in developing a machine learning method here.
Just give another sort of funny example, which is that like in one of the classes I was taking that was introducing me to machine learning methods and sort of this idea of garbage in, garbage out. There's this funny example that maybe you've seen before that if you train a neural network on images of like zebras and then ask it to like classify a zebra. So if you train it on, butchering this example, it's about zebras. If you train it on zebra pictures in color and then ask it to predict what a zebra, if it's a zebra in black and white, it's totally unable to do it because it's learned that zebras always have yellow backgrounds because they live on, you know, the safari plains. That was, sorry.
Do we have any audience questions? Someone over there first.
Hi, thank you so much for this panel. This has been really insightful. I was wondering if you have any thoughts about applying GPs to data sets that from instruments that have different band passes and the validity of actually doing that.
Belinda, do you want to take this?
Yeah, so I guess the differences with different band passes is that you're probing slightly different things of the stellar physics. I think it's possible. I think you're just sort of then probing a slightly more complex underlying Gaussian process. So if you're using appropriate activity traces, it would just increase the complexity of your model. But I think is something that can be handled. It's certainly, so the Pi90, for example, you do have a way of incorporating different instruments. And then part of the extra hyperparameters of that process is looking at instrument offsets and differences between the instruments. You'd probably want, there's ways of handling it. I think it's not impossible. I think it's, it can be done, but it just adds more parameters.
I think they're also, just building on what Belinda said, I think there are like different ideas in literature about how you can treat a GP that, you know, wants to simultaneously model activity signals in different band passes. So one, like maybe the simplest way is just treat these GPs as like scalar multiples of each other or linear combinations. So if you have like some different RV 0 point offset, and then like you have a visible spectrograph where you expect, since the spot contrast is larger in the visible, your RV amplitude due to your activity signal would be larger. So you could just imagine that you have, you know, two GPs, one of which is bigger because you're in the visible and one of which has a smaller amplitude because you're in the IR. I feel like I personally think there could be a lot more like inter instrument comparison of data sets and like seeing if this holds up, if we actually expect the two different two different data sets that are taken, simultaneously or near simultaneously with very different spectral bands, if we expect them to actually be scalar multiples or if there are sort of second order deviations. But yeah.
In the wide range of applications, you often see that there are many situations in which deep learning really like broke the market. So there are not, everybody knows a few examples. GPT is the latest one. Do you think there is an example like this in astronomy? And more specifically, do you think there's an example like this in like precision measurements in astronomy?
Okay, I have a crazy idea that so when I was doing this internship over the summer, I was trying to like rack my brain for any possible way I could apply a recurrent neural network, which is the thing that tries to like do autocorrect. And so the current large language models are a lot more complicated than the recurrent neural networks that I read about. But I was like, it'd be so cool if we could like, if I could find an application for a recurrent neural network. And so I was trying to think of a problem in astronomy or exoplanet RVs that's like fill in the blank type problem. And the crazy idea I came up with was, okay, you take like the entire HARPS data set and you just you train a neural network on this giant RV data set and have it fill in the RV. And so maybe if you do that, maybe the data set's large enough that it would learn stellar activity and it would learn spectral types and it would learn Keplerians. And I don't know if that would work, but if somebody wants to try it, let me know if it works. But yeah, I don't know.
So you were mentioning that one of the worries of machine learning, Gaussian processing, everything in general is making sure that people that use it understand what's going on, and that there needs to be an underlying understanding of not just the physics, but the maths of what's going on. But at the same time, we can easily admit that machine learning has a huge, it's really hard to communicate. The maths a bit too hard to just throw it at someone. So what do you think are the best thing? What could be good things to have and do in the future to make sure that machine learning, Gaussian process, neural networks become slowly more accessible to the entirety of the community while still preserving the need to understand what's going on?
I think that's a really good question. And I think part of that has to be what I think is already happening in a lot of universities, which is kind of the evolution of the classes that get taught to incorporate advanced statistics and machine learning techniques. I mean, I would argue that to some extent, understanding machine learning is a really good skill for everyone to have in the modern world, because machine learning creeps into a lot of the stuff that we do, and there's lots of biases and things in there that we'd like to understand. I'll say that I think that some of what is necessary in order to, say, implement a Gaussian process can be communicated pretty well through things like infographics and like toy model experiments, and going through tutorials like the ones in the exoplanet code, I think are a really great example. And so I don't know that you necessarily need to understand every bit of the math in order to understand the general concepts behind what's going on and therefore be literate in these concepts. But yeah, I think those are the answers. One, teach more, and two, make pretty pictures.
Yeah, I completely agree. And I would also add that I think we as a field need to financially invest in education at lots of different levels. I think at the undergraduate level and early grad student level, we're actually teaching classes. We also need to give people money to make pretty pictures and easily explainable things. So yeah, throw money at the problem.
Yeah, as someone who started in RV pipeline development and sort of more recently worked in deep learning. Yeah, I think those, pretty picture, I'll second to those pretty pictures. And I think just sort of having a general understanding is really the important thing. And I think you can do a lot with a black box that you feel like you understand, even if you don't understand all the math in it. I think when it comes to interpretability, there are ways to assess that without having the math all check out under the hood, because realistically, it's not going to anyway. You're going to make some sort of statistical assumption that that's gonna fall through if you try to make sure your model is ironclad. But you can validate it by comparing with other data sets, by comparing with other approaches, and by maybe for example with solar data we compare with other types of observations at the same time, images of the sun or something like that. I think those are great ways to enhance interpretability too.
Yeah, I really love this question because communication for me is one of my passions. Yeah, it is challenging. It is challenging to communicate these ideas, or at least I find it's challenging to communicate neural networks because there are so many neural networks talks that I've been to that I still don't understand what neural networks are. I understand a little bit more today, but every time I watch another talk on neural networks, I understand a little bit more each time. It's quite nice. But yeah, Gaussian processes, it's something that I've thought a lot about because I've had to give talks on it a lot. And I think the way that I explain it has evolved over time, and the use of graphics is definitely very helpful. In terms of really training up next generations of people, yeah, I mean, the maths is important, but I don't think you need to necessarily make people derive it from first principles. That would be mean. You don't need to do that to actually understand it. I don't think, at least I haven't done that because maths isn't my strong suit, but I still feel like I have through playing with it, through really getting my hands dirty with it, and really playing around with the quasi-periodic kernel, stretching it all sorts of ways. Yeah, I've been able to develop my understanding of how it works. And so I think yes, teaching the maths is important, but also giving people the opportunity just to play with these things is really good.
But I think, well, maybe we can do one more short question and then we should let people go to their coffee and posters and stuff.
Sure, I'll try and keep it kind of simple and short. So this is especially related to sort of what Sarah was talking about earlier. Do you think that there is more that could be done to, say, connect exoplanet astronomers with people, say, in the private sector, or something that are experts in machine learning stuff? Like, do you think that would improve our ability to do machine learning if we had a lot more of that?
Yeah, absolutely. Not least of which because people in the private sector have a lot of money and, love space. And so if we can convince people to give us money to let them teach us about all this stuff, that would be awesome. Yeah, I think I also think that in general, there are a lot of people in the private sector, especially in really big companies that want to help, but don't really know, wouldn't go out of their way to do something. So I think if we as a field just sort of started emailing people, we would probably have a lot more success at, initiating collaborations with people in industry that train neural networks every day of the week.
I share Sarah's optimism, but I do also think the point that Sarah herself made earlier about industry often having different goals in applying machine learning and not necessarily prizing interpretability is important to keep in mind when trying to borrow methods from them. So I think the key would be to find the people in industry who are truly interested in uncovering the science underneath these things and are willing to, work with us to meet halfway in the goals that the machine learning models have.
I'll just also make one more point that I think we could do more sharing of people between industry and academia in general. I think the sense that I get is we think of people going into industry and sort of staying there and never coming back into academia or vice versa. You're either in academia or you're in industry. I think there could be, I did an internship in industry. It was awesome. I would encourage every PhD student to do it if you can. I think those types of things would be really cool. We can learn and borrow techniques that way. And I think also like staying in touch with our colleagues who become data scientists and software engineers, I think would be really cool.
Yeah, I'll just second that. Let's not have a stigma against industry, but rather work with industry more. And I think there are, gatherings like conferences that industry machine learning people go to too, and maybe some astronomers could be sent there somehow to find industry people to collaborate with. I don't know how that would work, but I think there are channels in which that we could open up just through out of sheer interest. And from my own experience working with 2 data scientists, there's grant funding for that too. You could apply for a grant with somebody in industry and it might work. So yeah.
Yeah, I'd say, agree with all of these points. I'd also add, we should also talk more to the people who work in buildings next to us in the maths department, and in statistics and in all of those other fields that, they're doing the same things as us, but on different, in different ways. In Oxford, we collaborate with people in the maths department, and that's part of the project, developing new physically motivated kernels, working with those mathematicians to really understand how can we build something that is a proper GP kernel, but is physically motivated. So yeah, it's also talking to the people who are literally our neighbors and are right there in the same university or at other universities. Talk to everyone.
Amazing. Well, with that, let's thank our panelists again.